Welcome back. Today we'll look at paper 1, specimen paper 1A. Now, as always, this video might go on quite a long time, so feel free to watch at 1.25 or 1.5 times the speed. Right, question 1 says, a school network has several computers. Each computer in the network has a media access control or MAC address. Hexadecimal is used for MAC addresses, and part of a MAC address is, well, given below. Right, so each pair of digits is stored as binary in an 8-bit register. Right, complete the binary register for these two pairs of digits. Right, okay, so actually converting hexadecimal to binary, right, and vice versa is quite easy. Because what we do is, well, we just say that one hexadecimal digit is going to be 4 bits. And the reason for that is, well, 2 to the power of 4 is 16. And yeah, because of this relationship, what this is saying again, right, 4 bits is going to be one hexadecimal digit. So here then we just break them into individual, individual hex digits and then just convert them directly. So 9 in binary, well, that's going to be right 1001. 1001. Because if we think, well, we've got 8, right, then 4, then 2, then 1. Okay, and I mean then we're just going to write again, so 8421. And then the next 4 bits are going to be this 7, right, which is just going to be 4, 2, and 1. Now, likewise, if we want 5, I mean, that's going to be no 8s, right? There will be a 4, and yeah, there'll be a 1. And then for C, well, let's think in hex, right? A is going to be 10, B is going to be 11, right? Therefore, C is going to be 12. Of course, D is 13, E is 14, F is 15. So here, then, we just want to represent 12. And if we think, well, 12 is going to be an 8 and a 4. Right, then we want to describe what is meant by a MAC address. So let's say, well, it's going to be a unique address that can uniquely identify, basically the network interface card, right? So you can say it can kind of uniquely identify a device. So right, let's say an address, right, that can uniquely identify a device. And while like an IP address, well, that's just going to be unique on the network, okay, if it's a private IP. Now, public IP will be, globally unique, but a MAC address, a MAC address will be globally unique, right? So worldwide, right? So an address that can uniquely identify a device. Let's say globally. That's an L. Right, and then we can say probably a MAC address where it's going to be, well, like we saw here, right? In fact, well, hang on, yeah, that's just part of a MAC address. So a MAC address is going to be 12 hexadecimal digits. So let's say maybe consists. Consists of 12 hexadecimal digits. And then we can say the first 6 will be assigned representing the manufacturer and model. Right, and then the last 6 will represent, that particular device, right, all kind of unique for that device. Right, so the first 6 hex digits. Right, let's say they represent the manufacturer. Right, so the manufacturer and model. Right, let's say the last 6 hex digits, or yeah, just the last 6. Right, they represent, let's say a unique code for this device. Right, and then we can probably say it's going to be kind of like hard coded, sort of at the factory. So let's say, right, MAC addresses. Let's just say that, right, are hard coded, or we could say, built into the hardware. Or let's say, yeah, hard coded into the hardware. Right. So let's be more specific, right? Rather than saying hardware, right? Let's say hardware slash, and then it's going to be the network interface card. I don't know, like maybe at the time of production, I guess. Right, and then we can probably just mention that technically it's not impossible to change them, but you can say it's going to be difficult, right? Difficult / impossible to change. You know, whereas in contrast, like obviously an IP is going to be easy to change, because I mean, especially if you're using DHCP, then all you need to do is, well, turn off your, let's say turn off your device, right? And then when you reconnect to the network, I mean, probably you'll get a new IP address. Yeah, especially if, you know, other devices have connected in the meantime. Right, so anyway, for a MAC address, well, difficult / impossible to change. Yeah, or you could say, right, for the user to change, but I think that's okay. Right, then give 2 other uses of hexadecimal in computer science. Right, I mean, so I think a common one, I mean, you can just say colors, and maybe people have seen something like this. I mean, first they usually use the hash symbol, then they go, I don't know, maybe FF, let's say 00, and then like FF. So what you say is, well, let's say the first 2 hex digits, right, represent red, the next 2 are going to be green, right, and then, well, the last 2 are going to be blue, so just RGB. Now in this color, well, for this color, what we're saying is we've got a kind of, you know, maximum red, right, obviously 0 green, and then, yeah, maximum blue. So I guess red and blue, I mean, probably that's purple, I guess. So yeah, I mean, let's just say color codes. Right, and then if we think of another use, I mean, well, obviously they said MAC addresses already. I mean, we could mention IP version 6, because, yeah, IP version 6, that's also used in hexadecimal. But I think maybe a more common one, I mean, let's just say memory addresses. So yeah, you can say like memory addresses for error dumps, yeah, obviously IP version 6. Yeah, and obviously, well, MAC addresses, I think they would be the sort of main 4. Right, so another value is stored as a binary in a register. Right, a logical left shift of 2 places is performed on the binary value. Right, complete the binary register to show its contents after this logical left shift. Right, so I mean, well, the way I do it is basically, I think if we're shifting 2 to the left, you know, we can just kind of highlight these. Right, basically I mean, well, these 2 are just going to get shifted off. Right, then I mean, all of these 6 are obviously just going to get shifted left 2 places. So let's just write those down. Right, and so now in these 2 empty positions, well, what's going to happen then is you're going to have 2 zeros that are going to get shifted in. So yeah, that should be fine. Right, state 1 effect this logical left shift has on the binary value. So if we think, well, if we're shifting everything 1 position to the left, right, then it's going to double. If we're shifting things 2 positions to the left, right, it's going to times 4, obviously 3 times 8, and so on. So effectively we can say, well, it's going to multiply by 2 to the power of n, right, where, yeah, n is the number of, let's say the number of positions that we're shifting. Now, if we were going right instead, well, then it's just going to half, it's going to quarter, right, it's going to, you know, divide by an 8. So, I mean, here we could say, well, yeah, we could say it's going to multiply by 4. However, in this case, like, because we actually have this 1, right, and this 1 has got shifted off, then it's actually not going to give us the correct answer. So yeah, I mean, these questions are a bit weird when it says, you know, 1 effect, because I mean, I don't know, all right, let's say yeah, shifting left by 2 places. Yeah, all right, I don't know, all right, shifting left by 2 places. And let's say, I mean, should, right, so should multiply by 4. Yeah, I mean, so I think that would be enough, right? However, we can probably give more detail. So let's go, however, right, and we can say, well, because, let's say, because a 1 has been shifted out, the answer will be incorrect. So let's say, yeah, because a 1, right, has been shifted out. Yeah, let's say the answer is incorrect. Alright, yeah, I think that's okay. Right, so negative denary numbers can also be represented as binary using 2's complement. Right, complete the binary register for the value, right, minus 54. Right, you must show all of your working. So, I mean, well, there's a couple of ways to do it. I mean, first, let's try and just do it sort of in one step. So first, then we have to think, well, the first, or yeah, the most significant bit is going to be negative. Right, so minus 1 to 8. Yeah, then of course, well, 64, 32, right, 16, yeah, 8, 4, 2, and then 1. So because it's negative, well, of course, there has to be this minus 1 to 8. And then, I mean, well, then if we add 64, right, then that's going to get us to minus 64. So yeah, I guess that's okay, right? But then if we add 32, well, that's going to be too much. Right, adding 16, yeah, that's also going to be too much. Right, but then if we add 8, well, that's going to get us to, what, minus 56? And then I guess in this case, okay, we just need a 2. Right, and I would say, you know, you can check this if you want, just by adding this up again. So yeah, minus 128, right, plus 64, plus 8, plus 2. Yeah, that should be minus 54. Now, another way to do it is, well, what we can do is, well, we can just write down positive 54, which, yeah, this should be a little bit easier. All right, so I'm actually going to do it just below here. So what in this case it's going to be positive 128. And yeah, let's just write these down quickly. Right, so to get positive 54, well, there's, right, 0 128s, also 0 64s. Right, there will be a 32, there will be a 16. Okay, this will give us 48. Right, there won't be an 8, but there will be a 4, there will be a 2, and then, yeah, I guess there won't be a 1. Right, so yeah, that should be correct. And then, I mean, what we then need to do, well, we then need to flip the bits, and flipping the bits will get us the 1's complement representation. So flipping the bits, well, 0 becomes 1, yeah, and then obviously 1 becomes 0. Right, then what we do is we just have to add 1. So let's just write down 1 here. And, you know, you can see, obviously, this method is kind of, you know, more long-winded, but some people struggle, you know, just using negative like this. Right, so, I mean, basically here we can ignore this now. So what we're doing is, well, obviously we're doing this one, right, and then add this one. Right, so 1 plus 1, well, that's going to be 0, carry the 1. Right, 1 plus, yeah, 1's 0, 0. All right, that's going to be 1. Yeah, 0 plus 0 is 0. 1 plus 0 is 1. All right, then we've got a couple of zeros. Yeah, 1 plus 0. And then here, right, 1 plus 1. Sorry, yeah, 1 plus 0. And if we actually look at this, well, you see, right, so 1, 1, 1, 0, 0. Yeah, that's the same. And then, right, 1, 0, 1, 0. Yeah, that's the same. Okay, so both of these methods work. And of course, you know, in the exam, make sure to copy your answer right into this box. Right, a company has a website that is stored on a web server. The website data is broken down into packets to be transmitted to a user. Right, describe the structure of a data packet. Okay, so, I mean, let's try and do it here, for example. So a packet, what you're going to have, well, first you're going to have the header. And inside the header, well, you're going to have things like the IP address. And this will be both the source destination IP address, right, so like our IP address, also the destination IP address, okay, and then also, well, the packet number. I mean, you know, to be honest, there's also other things, but I guess for IG, right, that's all they want you to know. Right, and I mean, this one is a bit strange, but there's also going to be a trailer. Now, I mean, the reason it's strange is because, I mean, technically packets are referring to the IP layer, right, or the internet layer. Whereas actually this trailer, well, this is added in the data link layer, right, which is where they have, for example, Ethernet. Yeah, however, they do include this in the answer. Right, and then, I mean, here in the middle, well, then we've just got the payload, right, so the payload is the actual data. So yeah, let's just try and explain that then. So let's say, I don't know, maybe these, yeah, I know there will be a header. Right, there will be a header at the start of each packet. Okay, right, start of each packet. Right, let's say, yeah, that contains. Right, let's say the source destination, or let's say the source IP. Or let's say, yeah, IP address. Right, yeah, and destination IP. Or in fact, yeah, I mean, let's not go and. Right, so the source IP address, the destination IP, right, and packet number. Right, I think, yeah, then we can say, right, maybe then or next. Right, then there will be the payload. Right, let's say the payload, right, which is the actual data we're sending. I mean, yeah, we could say the application data we're sending, because well, if you think of the TCP/IP model, right, which is again not included for IG, but well, if you think like the application model or the application layer, that's going to include protocols well like HTTP or FTP, yeah, SSH, any sort of like video streaming protocol, right, all this kind of stuff. Right, so this is going to be the application data. And then I guess we can just say finally. Right, so finally there will be a trailer. Yeah, and to be honest, I'm not actually 100% sure what's in the trailer. Possibly there'll be a checksum, but I think the main thing, there's like a separator. I mean, we can just say, right, which will include data required for the, let's say the data link, right, or the Ethernet layer. Right, yeah, let's say for, I don't know, for the data or yeah, data link layer. Now, if you actually want to look at packets, right, and see the specific data that they're sending, well, there's a good program you can download called Wireshark. And yeah, I mean, this program, it's 100% free. So yeah, I mean, this is quite interesting, right? Or you just, watch a video about Wireshark. Yeah, if you're interested in, kind of exactly what's being sent in the header, right? What's being sent here in the trailer. Right, so the website hosts videos that users can stream. The company uploads new videos to the website. The videos are compressed before they are uploaded to the website. Right, tick one box to show which statement is a benefit of compressing the videos. Right, I mean, so data is encrypted. I mean, no, not really, because, I mean, the data is compressed, but then, I mean, well, basically anyone can decompress it, as long as they know the compression algorithm that was used. So yeah, I mean, this is not going to be true. Right, duration of each video will be reduced. I mean, well, no, this shouldn't be true, because obviously, yeah, you want to keep the video the same length. Right, less storage space on the web server. Okay, so yeah, this should be true. And then, well, more bandwidth is required when viewing the videos. So of course, this is the opposite, right? I mean, this would be less bandwidth. And yeah, I mean, here it does say only one box. Right, so give two methods of compression that could be used to compress the videos. Right, so I think the first one we can just say lossy. And then, yeah, obviously the second one is then just going to be lossless. So just to recap, I mean, lossy, well, this means that some of the data will be lost. So let's say, I mean, I don't know, this is our original video, right? We would then compress it. Obviously, well, the video is going to get smaller, right? But then when we decompress it, well, we won't be able to get the original video back. Obviously, we're going to lose some quality. Whereas with lossless, of course, well, we compress it, right? Then when we, decompress it back, of course, yeah, now we can obtain the original value. We can obtain, the original video still. So, I mean, you can say, well, obviously, the advantage of lossless, well, it's going to be higher quality. But it's not going to compress as well, right, compared with lossy. And for example, something like if we're talking about videos, I mean, something like MP4, right? So MP4 is going to be lossy, and I think they say I mean, this can achieve a reduction of like 200 times. So rather than having a video that's like terabytes, you can have like a 2-hour movie, and yeah, this can be like an HD movie, which is what 2-3 gigabytes. Whereas, yeah, if it was uncompressed, this would literally be terabytes for that same movie. Right, the company uses parallel half-duplex data transmission to transmit the data, right, for the new videos to the web server. Right, explain why parallel half-duplex data transmission is the most appropriate method. Right, so I guess, well, we can say parallel because it's going to be faster, right, faster than serial. And then I suppose half-duplex because, well, I suppose in this situation, they're saying they only have to send, or well, they only have to upload videos. And then I guess once they've uploaded the videos, right, then people can start downloading them or start watching them. But they're not having to be uploaded and downloaded at the same time. Now, if you wanted to upload videos, and other people to download them at the same time, well, in that case, you would then need full duplex. But yeah, I suppose here, I don't know, their server is quite simple. I guess they don't need that functionality. Right here, so let's say parallel can be used. Right, parallel can be used. Oh yeah, parallel transmission can be used. Right, since it's faster. We can say, right, it's faster than serial transmission. Right, so faster than serial data transmission. Yeah, okay. Right, and well, let's explain that, right? So because, and I mean, yeah, here it does say explain, right? And well, here, you know, because multiple bits can be sent simultaneously. Right, okay, and then we can say, well, half-duplex. So let's say half-duplex can be used. Well, again, I suppose because we're saying they only need to upload, right, or download, right? They don't need to do both at the same time. So let's say, yes, since for this situation, let's say, I don't know, maybe the user, yeah, or, well, I guess we can say the company. Alright, so the company only needs to either upload videos or download videos. Right, or download videos. Okay, but not at this, or yeah, but not both at the same time. Right, and then, I mean, I noticed they did actually give one more in the mark scheme. So, I mean, well, yeah, I don't know. I mean, here they said that skewing won't be an issue because, I mean, there's a short distance. However, I'm not sure how they have actually sort of determined that there is a short distance. And you know, when I say a short distance, I guess between between the uploader and the server, like, yeah, because I mean, it doesn't really mention that anywhere, I don't think. I mean, for example, you know, it doesn't say they're in the same room as, you know, the server, for example. But I guess, well, their argument then is that somehow they know there's a short distance between the uploader and the server, and because of that, you're not going to get skewing. And let's say the problem with skewing, right, if we just have here, like, these are the parallel wires. Now, let's say, I know we've got some bit here, right, another bit here, another bit here, and let's say another bit there. Now, let's say, for example, I mean, I'll just write these as like relative speeds. So let's say this has a relative speed of 1, right, so the wire is just operating at normal speed. Now, let's imagine this second wire is going at like 0.8, so, you know, obviously it's a little bit slower. Maybe the next one is, you know, 1.2, right, the next one is, you know, 1.1. Now, of course, because these wires, they're transmitting data at, you know, slightly different speeds, yeah, maybe because of some, you know, hardware issues or something, then obviously after a while, what's going to happen is, well, they're going to get out of sync, where you might have, let's say, you know, the 10th bit, let's say, I don't know, like the 10th bit in this kind of row 1 is going to arrive at the same time as, well, here, you know, the 8th bit, you know, obviously in this, you know, line 2 or wire 2. So again, right, this is called skewing, and obviously, yeah, this is going to be a problem with parallel data transmission, which is going to be one advantage, right, of serial data transmission. Yeah, but I don't know, like in this case, they're saying because there's a short distance, which again, somehow I'm not sure how they know that, because there's a short distance, then, you know, you can kind of ignore skewing, because yeah, skewing is only really going to matter over long distances. Right, so the company's concerns about a distributed denial of service attack explain what is meant by a DDoS attack. Alright, so I mean, let's try to just draw this quickly. So in a DDoS, well, you're going to have, let's say, like a hacker, right, let's call them H. They're then going to have bots. So, I mean, these bots, well, they're just computers that, you know, they've hacked or they control. And I mean, these bots, well, this whole thing is going to be called a botnet. Then what you'd have, well, you then have the server, right, so this is the website. And like when the hacker tells them to, right, these bots would then all just start, you know, bombarding the server with traffic. So sending them, you know, like thousands of requests per second. And then, well, then if you have, let's say, like a legitimate user, I mean, let's just call it, I don't know, C, like the client or someone, right, when they try to access the server, well, probably the server will just time out because, you know, the server is busy, like handling all of these requests, you know, from the bots in the botnet. Because again, if these are sending like thousands of requests per second, right, then, you know, this client, well, their request is going to be like the kind of back of the queue. Yeah, it's not going to get served. Right, so let's just try and explain that then. Let's say maybe a hacker, right, or you can say like a malicious third party, right, maybe has installed, or I don't know, maybe has managed to install malware, right, let's say on victim computers. Yeah, which I don't know, we can say, right, which they now have control over, right, so yeah, which they now, I don't know, yeah, have control over, or kind of which they now can maybe issue commands to. Right, so let's say, I don't know, yeah, so I don't know, like the hacker can issue a command. Right, I mean, or we can say, I mean, right, so let's kind of explain, yeah, this term botnet. Right, so let's say these infected computers are called bots, or yeah, infected devices, because I guess it could be a phone or something. Right, infected devices are called bots. And let's say, right, and make up a collective botnet. Right, let's say, so the hacker can issue a command, or yeah, maybe let's say, right, the hacker can instruct, right, the bots, let's say to, like, I don't know, to send mass traffic, or maybe, yeah, mass requests, right, to the target or / victim server. I mean, well, so here they mentioned company, right? So let's say to the company server. Yeah, okay. I mean, well, let's just say, right, which can overwhelm it. Right, and then let's mention, let's say legitimate users might not be able to connect. Right, legitimate. Yeah, let's say legitimate users might not have their requests served. Right, so yeah, might not be able to have their requests served. Right, and, well, the reason, let's say because, yeah, the server is overwhelmed with the botnet's requests. Yeah, or let's say the server is, I don't know, yeah, I think overwhelmed is okay. Right, so overwhelmed with the, I don't know, yeah, the botnet's requests. I think that's fine. Right, so suggest one security device that can be used to help prevent a, well, DDoS attack. Right, okay, so I mean, from the company's point of view, well, basically you just have a firewall. So if you put a firewall in front of the server, well, that can then, you know, filter out some of the traffic. So if, for example, you notice that, yeah, I know you're having like some IP address that's sending, you know, 1,000 requests per second. Well, of course, well, you can either you just limit that IP address and say, okay, look, hey, you can only send, you know, 1 request per second. Yeah, or you just completely blacklist them, right? Just, you know, completely block them. So yeah, I think firewall is going to be the best one here. Yeah, and I think really a firewall is kind of the only way. I mean, in terms of like for the user's computer, well, of course they can run anti-malware, you know, on, again, you know, on these users' computers. But obviously, I mean, the company doesn't actually have sort of, yeah, any way to like enforce that the users run anti-malware. So yeah, I mean, from the company, right, a firewall is kind of all they can really do. Right, a web server has an internet protocol or IP address. Give 3 characteristics of an IP address. Alright, so I mean, let's just write an example like 111, maybe 222. Alright, let's go 50, and then like, I don't know, 255. So if we see here, well, we say there's what, 4 groups of denary numbers. So yeah, let's say that, right? Maybe 4 groups of denary numbers. Right, and let's probably say, yeah, each group, right, can, I don't know, can be in range, and then 0 to 255. Right, and then, I mean, well, we can also mention they're separated with a dot. yeah, so let's say right, groups are separated with dot. Yeah, or like period, right, dot, full stop. So I think that, those should be okay. Now you can also probably mention the length, right? So the number of bits. So if you think, well, each group is going to be 8 bits, which means therefore that the whole thing is going to be 32 bits. I suppose, this is for an IP version 4 address. Now here they actually don't specify if it's IP version 4. But I guess, just the default, right? Probably they're referring to IP version 4. Yeah, I don't know, like for this, like maybe you could also mention things like, well, it can be public, it can be private, right? It can be dynamic, it can be static. Yeah, things like that. Yeah, probably you can mention again, it can let's say it can uniquely identify a device on a network. That would probably be accepted as well. Right, so identify the network component that uses the IP address to send data, right, only to its correct destination. All right, so here then, well, let's try and draw this. So here we're going to have the client, right here we're going to have the server, and then, on the path, right, you're just going to have these things. So hopefully, right, these are just going to be the routers. So, the client, well, let's say you've got some file, it's just going to break up this file into packets. And then let's say, I don't know, maybe the first packet might be sent to this router, right, then it might be sent to this router, right, then, to the server. Let's say another packet might be sent a different route. Right, so this is like packet 2. Yeah, and then maybe it goes here, then it goes here. Yeah, then it goes to the server. So that's the whole point, right? The packets will be, well, let's say the file, or I guess file, right? The data will be broken up into packets. Right, the packets can then be sent along different routes because, like, I don't know, maybe let's say this router just stops working. Well, of course, then the next packet could then be sent to this router. And then obviously, sent to the server like this. Now, what can happen then is, well, the packets can arrive out of order. Like, let's imagine you have, I don't know, packet 1, right, then packet 3, then packet 2. Well, of course, this is in the wrong order, so the server then just needs to, rearrange these right into the correct order, when it receives all the packets. You can also have a situation where, let's say, I don't know, hang on. Let's say we get packet 1 and we get packet 3. Okay, but we don't receive a packet 2. Well, in that case, obviously there's been some transmission error, right? Some of the packets have been lost. And in that case, well, the client then obviously has to resend those packets. So yeah, this is the two things that a packet number is used for, right? Both kind of reordering the packets into the correct order, at the destination. And then also obviously determining if any packets have been lost. In which case they can be resent. Right, so yeah, this then is just going to be router. Right, the website has a uniform resource locator URL, an example URL, right, Cambridge Assessment, right, .org.uk/index.html. Right, complete the table to identify the name of each section of the URL. Right, so HTTPS, well, this is going to be the protocol. And if we think, P literally means protocol, because again, right, this is what hypertext transfer protocol. And then, this S just means secure, right, so it's encrypted. Right, so let's say protocol. Right, the next one, so, well, this is just the domain, right, the domain name. Let's say domain name, that should be fine. I guess, technically you'd actually, this org.uk, right, that's going to be the extension as well. But yeah, I guess here we can call the whole thing the domain name. Right, and then this one, well, this is the, let's say the path, or the, file path. I think path would be okay. Because what this is saying, get this index.html file, on the, sort of from the website, Cambridge Assessment, right, .org.uk. Right, computer has a von Neumann architecture. Circle 3 components that are part of the central processing unit, CPU, in this computer. Okay, so if we think, well, right, one is going to be the accumulator, because what this will do is, it's going to store the result of, let's say, arithmetic and logical operations. So let's say we do an addition, or we do an OR, an XOR, an AND, like any of these operations, right, the result is going to be stored in the accumulator. Obviously hard disk drive, well, this is going to be secondary storage, and in particular, it's going to be magnetic secondary storage. Right, so the memory address register, well, this will be something inside the CPU. And what this will do is, well, this will store the address that either you're about to read from, right, or the address that you're about to write to. Yeah, okay, well, right then the next one's going to be the program counter. And well, the PC, the program counter, that's going to store the next address, okay, I mean, well, let's say, yeah, the address of the next instruction, right, that's probably a better way to say it. Right, I mean, so random access memory, of course, that's primary storage. Yeah, read-only memory, again, right, primary storage. Well, sensor, okay, and then well, solid state drive again, so that's secondary storage. Yeah, and in particular, right, it's going to be solid state secondary storage. But yeah, of course, right, well, 1, 2, 3, right, these are going to be the correct answers. Right, so describe the purpose of the control unit within this computer. Right, so the control unit, I mean, this is going to be the thing that kind of manages the CPU. So let's say that, right, the control unit. Yeah, I mean, I don't know, let's say like manages the CPU. And let's say, right, being more specific, so for example, right, so this is going to, well, it's going to emit the clock signals. So each, because, you know, the system clock is going to be inside the control unit. So each time the clock ticks, right, or the system clock ticks, well, yeah, that clock signal will be sent out by the control unit. Right, so let's say the system clock signals. Right, it's also responsible for decoding the instructions. Right, and I guess, yeah, we can say maybe sending control signals. Yeah, so let's say, right, sending control signals. So this can be things like interrupts as well. And then I think finally, let's just say maybe allocating, or let's say like allocating responsibility to specific hardware to execute the instructions. Alright, so yeah, let's say maybe allocating execution, right, of instructions. Yeah, let's say to specific components. Right, I mean, so just to explain some of this, I mean, let's say decoding instructions. Now, let's imagine we have an instruction set, and I don't know, maybe we've got add, right? And let's say add is going to be represented by the binary 4 zeros. Let's say we've then got LDM, right? So this is going to be, well, load immediate. So basically, this means, well, just like loading a number right into the accumulator. I mean, let's say this is represented by, you know, the instruction 001, and let's say then we just got store, right? So kind of, you know, writing the data or saving the data. And let's say this here is just going to be instruction 2. Now, let's say then we have an let's say we have some instructions like this, where, I don't know, maybe the first one is like 000. Right, so this here is going to be the opcode. Right, then the operand, well, this is going to be the actual data for this instruction. So I don't know, let's say we just got a 0011, something like that. Or in fact, hang on, sorry, let's actually make this, yeah, let's make this 1. Right, let's say we've got another instruction. Let's go instruction 0, or yeah, opcode 0. And I don't know, maybe let's just make this like that, I guess. Right, and then let's just say the next one, that's going to be 00, right, 10, and let's just go right, 1 like this. So if you see then, well, our first instruction is going to be this one. So what we have to do in order to, you know, decode this, the control unit is going to look at the first 4 bits. And I mean, well, here it's 4 bits because, you know, our instruction set, the opcode is 4 bits. Now, you know, probably in a real computer, I mean, yeah, the opcode is going to be bigger, maybe, I don't know, 16 bits or 32 bits. Yeah, maybe 64 bits, you know, I'm not sure. Yeah, or that, well, I guess, yeah, not 64 bits, right, that's going to be too big. But anyway, right, so we've got this opcode, and we see here this opcode, well, 0001, right, so that's going to be this LDM instruction, right, 0001. So what this is saying is, well, here then we're loading the value 3 into the accumulator. So let's say the accumulator, well, this has the value 3. The next instruction, well, you know, these 4 zeros, right, that's going to be this add. And what we're doing, well, we're adding the number 4. So if you think, well, we've got 3 in the accumulator, then we add 4. Right, so now the accumulator is going to hold 7. And then finally, we've got what, 0010, right, so that's 2, right, this store instruction. And we're saying, well, we're storing this in memory address 1. So let's say here, this is memory address 1. right? Well, then this 7 is then going to be written, into this memory address. So I mean that's what it means when we say decoding, right? I mean you're taking the whole instruction, and you're basically working out, well, yeah, which part is the opcode, which part is the operand, like which, let's say which instruction does this opcode represent? It's going to be looking at things like addressing mode, right? What's the value of this operand? All this stuff really. Right, then we're also allocating execution of instructions to specific components, because let's say, for example, we've got an add. Well, we want to think, right, what component is going to do that add? And then what, in this case, this is going to be the ALU, right? So the arithmetic and logic unit. So the control unit will, send a signal to the ALU, right? Basically telling it to do an addition instruction. Whereas if we think, for example, the LDM or STO, well, I mean, these are going to be memory, right? Because either we're loading data from memory, right, or we're writing data, into memory. So here then it's just going to send a data to memory, and I mean this could be the cache, it could be, it could be RAM, right, but just some kind of memory. Right. Anyway, the next one, the computer has a single core CPU. State one purpose of a core in a CPU. Right. So a core is just going to be used to execute an instruction. So yeah, let's just say that. So I don't know. Let's say, right, a core, can execute instructions. I mean that's its purpose, and basically each core is going to have its own copy of like all the different registers. So the PC, the MAR, the MDR, CIR, right, also things like the ALU, right, the accumulator, all of this. So if you've got 4 cores, right, a quad core CPU, then effectively you've got 4 program counters, you've got 4 ALUs. Everything is just duplicated inside each core. And I mean, well, the reason it's duplicated is because you think, each core can be executing different processes, right? So, different programs, basically, right? Different processes. So, like, I mean, I don't know, like maybe in core 1, right, you're currently at the instruction 100. So, let's say program counter in core 1 has the value 100, but, program counter in core 2, right, might have, the value 500, because, of course, obviously it's, for a different program, right, a different process. Right, so the computer is upgraded to a dual-core CPU. Explain how the upgrade can affect the performance of the computer. Okay, so we can say, let's say, the upgrade. Or let's say the upgrade will increase the speed of the computer. Or let's say increase the speed of the computer. Right, and the reason for this is, well, if you've got 2 cores, effectively then you can have, parallel execution or simultaneous execution. Right, since, let's just say that, right now, let's say 2 instructions, can be executed simultaneously. So of course, each core is only doing 1 instruction, but since we've got 2 cores, then of course, 2 instructions can happen at the same time. So I guess what the upgrade can or might increase. Right, I mean, is that enough for 2 marks? The upgrades, might increase the speed of the computer. I guess, well, since we now have 2 instructions that can be executed simultaneously. I think that's probably okay, right? Because you say, well, increase is probably 1, then may execute it simultaneously. Right, that's probably the 2nd mark. Next, it says the computer uses a bootstrap. Tick one box to show the part of the computer of which the bootstrap is an example. Right, so application software. Well, I mean, let's think what the bootstrap is. So, I mean, when you run the bootstrap program, what it's going to do is going to load the operating system, from secondary storage. Right, so I don't know, maybe like your, let's say we've got some hard drive or something. Right, so basically it's going to load this operating system, from your secondary storage, and then just load it into RAM. Okay, I mean, that's what the bootstrap process does. And I mean, this is going to happen every time you turn on the computer. Right, so it's not going to be application software because, well, that's the high-level software, for example, web browsers, games, like Office software. Right, I mean, firmware, so this will be the low-level software close to the hardware. So I mean, I think, this seems correct, but let's read the others just in case. I mean, well, hard disk drive, I mean, well, this is obviously hardware. And then, yeah, MAC address, I mean, again, that's related to networking. So, yeah, definitely firmware here. Right, so a programmer uses a high-level language to create a computer program. Identify 2 advantages to the programmer of using a high-level language instead of a low-level language. Right, so I think, I mean, let's just say maybe easier to understand. And I guess we can say, you know, since it's closer to natural language. Right, I mean, I think the second one, I might say something like maybe more libraries are available. So if you think a lot of high-level languages, you know, they have a lot of libraries you can just use. Whereas, you know, low-level languages like assembly, well, yeah, I mean, you don't have access to all of these libraries. So, I mean, well, let's say that. Yeah, I know, like more libraries available. Right, let's say to easily and quickly develop advanced features. Yeah, and obviously, I mean, the advantage of using a library is that, well, hopefully it's been, you know, tested well. Right, advanced features. You know, especially if this is a library that, I don't know, maybe it's like sort of backed by some company, or it's, yeah, it's got like millions of users, you know, it's been around for a long time. Right, obviously that's going to be well tested. Whereas if you try to write this code yourself, well, maybe the code is going to be extremely difficult, you know, you're going to make mistakes, there's going to be bugs. So yeah, that's the advantage of using a library. Right, suggest one disadvantage to the program of using a high-level language instead of a low-level language. Okay, so, I mean, you could mention that possibly it's going to be slower. Right, so you say, yeah, possibly you can create a, you know, low-level program that's going to be faster, right, and also use less memory. But again, I mean, that just depends on, well, like who's better, right? I mean, is the programmer better, you know, programming low level, right? Or is the compiler better at converting from high level into machine code, right? And, you know, in reality, like probably the compiler is going to be better. I mean, certainly than me. And yeah, probably, you know, most other people, right? I mean, unless you're some kind of expert in assembly. So I think, I mean, that's not the best reason. I mean, let's go for one that's definitely kind of always true. And that's that in low level, you can directly access the hardware. Whereas, right, so yeah, in high level, you can't. So let's just say, right, high level languages, or let's say don't allow direct access of hardware. All right, yeah, high level languages. All right, don't allow, yeah, direct access of hardware, right? For example, registers. Yeah, alright, so I mean, let's say like e.g. registers. Right, then the programmer uses an integrated development environment, IDE, when creating the computer program. Right, state what is meant by an IDE. So I guess we can just say a software program. Yeah, let's say a software program that makes it easier for, I mean, let's say, yeah, that makes it easier to write programs or easier to write code. Right, makes it easier, yeah, okay, easier to write code. And then let's say, I mean, we probably say, right, usually, or I guess, yeah, kind of always contains. Right, usually contains, and then, well, one, there's always going to be a code editor, right, so obviously somewhere we can type our code. Probably there's going to be some sort of debugging features. Yeah, I mean, usually. Let's say, for example, syntax highlighting. Yeah, and I mean, you know, I guess for this you can go on, right? You can say like pretty printing. You can say you know, code suggestions, auto completion. Yeah, obviously just, you know, more and more. I mean, some examples of IDEs. You know, hopefully people are familiar with some of these. I mean, I guess yeah, I mean, I guess a common one is VS Code. And yeah, I mean, VS Code these days is, you know, super popular. To be honest, I mean, I would actually say the the JetBrains products are probably the best. In terms of like the amount of functionality, right, and the kind of error detection, things like that. So for Java, I guess you've got IntelliJ. For what Python, you're going to have PyCharm. I mean, if you're doing VB, then I guess what VB is going to be Visual Studio, right? Also by Microsoft. And then of course you've got other, you know, old ones like Eclipse. Yeah, I think some people use Idle, right, for Python. Although from what I've seen, Idle is literally just like a command line or text editor. Yeah, just kind of really basic. So I wouldn't really suggest that. You know, I think for Python, because a lot of people are doing Python, right, PyCharm is probably the best. Right, so robots are used in a factory to build cars. One characteristic of a robot is its mechanical structure. State 2 other characteristics of a robot. Right, so the way I remember this, well, just the initials, right, PEM. So P is going to be programmable. Right, E, well, electronic, right, so it's made using, you know, electronic components. And then what M, right, is going to be mechanical, so it has, you know, moving parts. Right, so yeah, here, well, let's just write that. So programmable. And then I don't know, maybe explain, right, can be programmed. Yeah, I guess that's kind of obvious, right, in the name. And well, yeah, I mean, let's just explain this a bit more. So let's go, right, can, or I mean, probably will. So yeah, will contain electrical components. Or yeah, maybe electronic components. Right, then we can say e.g., right, so e.g. microprocessor. Yeah, you can say what microprocessor, you know, input, output, right, memory, things like that. Right, so suggest 2 advantages of using robots instead of humans to build cars in a factory. I mean, well, I guess we can say speed. Yeah, let's say robots are faster than humans, right, probably faster than humans. Right, faster than humans. I mean, you could possibly say things like it's cheaper, or in the long run it's cheaper, because yeah, you don't have to pay, you know, you obviously don't have to pay the wages. I think maybe I might say quality control, or you can say like, yeah, consistency, I guess. Right, quality. So we can say what robots, let's say maybe robots can produce more consistent results. Yeah, often with higher accuracy. Maybe, right, more accurate. Yeah, let's say more accurate / consistent results. Yeah, and I guess, I mean, if you did want to think of other ones, again, you say, you know, probably the long term is going to be cheaper. I think often they mention safety, because if you've got, I don't know, maybe you're painting. I mean, let's say here, right, you're building cars, so obviously you've got to paint them. And I mean, for humans, it's quite dangerous, right? You know, breathing in those like toxic fumes. Yeah, and that's why you have obviously the, you know, robot that paints them. Right, so the Unicode character set is used to represent text that is typed into a computer. Right, describe what is meant by a character set. So if we think a character set, I mean, like, well, I'm not going to do all of them, but for example, we say big A is going to be 65. You know, obviously big B, right, that's 66. Let's say small a, right, that's, you know, 97. I mean, what we go big Z, that's going to be 90, yeah, obviously, etc. I think what 0, that's going to be 48. So I mean, yeah, these are the ones that they sometimes want you to know. Because, and you know, the thing that's easy about it is like, well, if you know that 0 is 48, therefore, if someone says, well, what's 5, right? I mean, you literally just count 5 places or just add 5. So in that case, we would know 5 is therefore going to be 53. So, I mean, what we can say then, a character set is, well, it's just a mapping, you know, from a character, right, to a kind of binary value. And yeah, we want to say this is a unique binary value. I mean, yeah, let's say that may be a mapping. Right, let's say between characters. Yeah, right, let's say, yeah, and a unique binary value. Yeah, I mean, I think that's all you really need for the general description. I mean, we could mention, I don't know, like, for example, Unicode can represent, you know, all the languages, emojis, right, etc. Right, Unicode can represent so all, well, I guess kind of all of the main sort of languages. Represent all languages, emojis, let's say symbols, right? So like mathematical symbols, right, etc. And to be honest, actually Unicode, I mean, this even has, say, things like ancient languages that like literally no one knows what they are, but I guess they just found it on some like scroll or some cave painting, and I mean they've literally just included this in Unicode, right? Even though no one knows what these symbols actually represent. Right, so one disadvantage of using the Unicode character set instead of the ASCII character set is that the text stored takes up more storage space. Right, give one reason why it takes up more storage space. I mean, to be honest, this is not always true. Like, let's say if you're typing in kind of, like the Latin alphabet, so just like A, B, C, just the sort of the digits, right, common punctuation, things like this, then actually in this case, well, both ASCII and Unicode would be the same. If you're using UTF-8, right, because if we think, well, UTF-8, this is going to use between 8 and 32 bits. Now, all of these kind of common characters, things like these, all right, I mean, they're only going to use 8 bits. Now, some other languages, let's say, let's say languages that have, more characters, right, they're going to use maybe 16 or 24 bits. Some of the emojis, right, they can use 32 bits. But let's just say this generally. Let's just say then Unicode uses between 8 and 32 bits per character. Or let's say Unicode represents more characters. Right, let's say hence needs between 8 and 32 bits. Or let's say 8 to 32 bits are required per character. Right, and then we can say, maybe in contrast. Let's say in contrast. Right, and then ASCII, hopefully you remember this, but ASCII requires just 7 or 8. Alright, let's say 7 or 8. So again, if you don't know, well, 7 bits would be standard ASCII, right? So that can represent 2 to the 7 different characters, which is 128. Now 8 bits, similarly, right, that's going to be 2 to the power of 8, which gives us 256 different characters. Right, so draw a diagram to represent how virtual memory is created and used. And I think I was going to say, actually, like, there is a good video about sort of Unicode ASCII, and I think he's called Tom Scott. So maybe if you type in like Tom Scott Unicode ASCII, there's a good video, right, for anyone that's curious about this. Right, so 8, we want to draw a diagram to represent how virtual memory is created and used. Right, okay, so let's say here maybe we can have our list of processes. I don't know, maybe let's say, like processes. But these are kind of the processes we want to run, right? So maybe we say, I don't know, A is going to take up this, let's say B is going to be here. Let's have 2, right? Let's have C, and then let's have D. So what we're going to have, let's then have RAM. You can call it RAM, you can call it main memory. Right, and then here we'll have our virtual memory. Okay, so this will be our secondary storage. And let's say virtual memory. And then I think in brackets I'll just put secondary storage. Right, so what we can say, let's say if this is a hard drive, part of this hard drive will be allocated, part of this hard drive will be partitioned. So let's say this. Basically, right, they call this the swap file, so let's just say this. And what the swap file is, well, this is the part of the hard drive or part of the SSD that's used as virtual memory. So let's say swap file partition. And when we say partition, this just means split, because what we're saying is, well, this part here, this one, right, this is going to be, the virtual memory part. and then everything else this 2. Well, this is just our regular hard drive that we can obviously use for files, programs, right, whatever. Right, so let's say maybe this A, right, this can be mapped into this position here. I mean, let's say, yeah, I don't know, I mean, let's say B can go here. Right, and then, well, let's just say D can go here. Oh, yeah, sorry, C can go there. Now, if we want to load in C, so maybe let's just write list. Yeah, well, let's say, right, try to load process D. And then what's going to happen, I guess, I don't know, maybe, yeah, I mean, let's sort of label that. It's not very good, to be honest. Right, what's going to happen then is, well, this C, or yeah, maybe this B, right, this can be swapped out to the partition. So let's say maybe this B, yeah, this will be put in the swap file, or yeah, paged out. So let's say, right, B, yeah, is not required. Right, let's say yes, so paged out. So I mean, you can say paged out, okay, you can also say swapped out, that's fine. Right, so then it means we can then load D into this position. Right, I mean, yeah, D can be loaded. Yeah, I know, like where B was, basically. Yeah, and then, I mean, I guess that's fine. We could sort of draw another arrow. Let's say, I don't know, yeah, B can be swapped back in if needed. Or yeah, let's say with another process if needed. Yeah, okay, so I think that should be fine. Right, although, yeah, I think I did also mention a good video about this. So there's another guy, right, his channel is literally just called Computer Science. And if you search, for example, like computer science, maybe paging, or yeah, so I think if you search, right, computer science paging, virtual memory segmentation, right, search all as that as, one string on YouTube. And then, yeah, you should find this video by, again, this computer science channel. And yeah, that will explain this quite well. Right, a student is using software to create 3D models. This process often requires the use of virtual memory. Right, explain why virtual memory is needed for this process. Okay, so we can probably say, well, one, I mean, the software used to create the 3D models is, probably going to be quite big. Maybe people are familiar with something like Blender. Yeah, I think another one is like Cinema 4D. I think there's also Maya. There's, yeah, I think other ones as well. But I mean, these programs, they're like, gigabytes upon gigabytes. I guess also the 3D models can also be quite big, like especially if there's some sort of, I don't know, I mean, yeah, some of them if they're animated, although here, yeah, it's probably talking about maybe just stationary. Right, so, yeah, let's say that then, let's say the programs, yeah, let's say the programs to create the 3D models. Right, let's say, yeah, and the models themselves. Yeah, let's say, right, are probably quite big. Right, and let's say yes, right, let's say so might not fit in RAM at the same time. And obviously, like, especially when you think, well, you've probably got a web browser open, you've probably got some, some other files open, right? Who knows? Right, so might not fit, yeah, fit into RAM. Right, let's say, yeah, to solve this. Right, let's say maybe, yeah, unused. Right, so unused processes or unused pages. Right, I mean, let's say pages. Right, so unused pages can be swapped, or well, we can say paged out. Right, so swapped out or paged out. Right, let's say swapped. Yeah, from let's say from RAM into virtual memory. Right, into virtual memory. Right, in order to make room for the program and 3D models. Right, okay, yeah, 3D models, and I mean, I guess we can say, sort of things in the virtual memory can be swapped back in. I mean, so right, let's say pages. So pages in, virtual memory. Right, let's say, can be swapped in if required, or can be paged in, if required. Alright, so yeah, that should be okay. Right then, 9, complete the sentences about symmetric encryption. Right, some of the terms in the list will not be used, you should only use the term once. Right, so first of all, let's go through all of them, okay, explain what they are. Right, so algorithm, I mean, you can say, well, this is basically just a list of instructions, used to solve a problem, or to perform a task. Right, a cipher, well, a cipher is going to be a specific type of algorithm. And in particular, it's going to be an algorithm that, well, let's say an algorithm used to encrypt data. I mean, well, copy, I think delete. Right, so key. I mean, a key is basically going to be, I mean, you can say like bytes, right? It's going to be data that's used to encrypt the data. So what you would have then is, well, you'd have the cipher, right? And then, well, the cipher is going to require a key, right? I mean, you can think almost kind of like a password. But yeah, I mean, this key will be used to obviously, encrypt the data, right, to scramble the data in a certain way. And then, right, you would then need a key in order to decrypt. Right, well, plain, so I think when they're saying plain text, I mean, plain text is going to be the unencrypted data, right, and then, well, ciphertext, that will be the encrypted data. Right, I mean, so private, I mean, that's also asymmetric encryption. Yeah, well, I guess, well, private key, right. So, I mean, a private key is going to be something that, well, obviously it's private, right? You're not going to give it to other people. Whereas a public key you will share with other people. And the reason you share it is because, well, you share your public key, and then other people use your public key in order to encrypt information and then send you that. And then, I mean, because you're the only person with the private key, then you're then able to decrypt, the message that they've encrypted and sent to you. But yeah, no one else will be able to decrypt it because, again, you're the only person with that private key. Right, so standard, I guess that's just like an, I mean, you can say encryption standard, which is kind of like a method. I mean, obviously stolen, yeah, maybe the key is stolen. Right, yeah, understood, unreadable. I think that's fine. Right, okay, so the data before encryption, right, this is known as the plain text. Right, to scramble the data and encryption. Right, okay, so I mean, here you could say cipher, you could say algorithm, but then it says which is a type of something is used. So I think here we say, well, cipher. Right, so a cipher is going to be a type, a type of algorithm. Because I mean, if you think algorithms, you can have sorting algorithms, searching algorithms, right? You can of course have cipher algorithms. Yeah, I mean, hang on though. It does say we should only use a term once. Right. So, well, the data after encryption is known as the right. So this is the ciphertext. Right. I mean, so yeah, I don't know. Like, I think maybe this one they say key, which is really strange, but yeah, because I mean, a key is not a type of algorithm. But anyway, all right, let's look. So encryption prevents the data from being, well, stolen by, I mean, okay, right, so not stolen by a hacker, because a hacker can still steal the data, but I guess, yeah, being understood by the hacker. Because, for example, let's say they do like a man-in-the-middle attack, right, or somehow they get access to your computer, well, they can still see, the ciphertext, but if they don't have the actual, decryption key, right, then they're not going to be able to actually decrypt it. The last one, it says, an art gallery uses secure circular SSL to provide a secure connection when selling art on its website. Right, we should describe the process of SSL and explain how it provides a secure connection. Right, so I mean, this one is difficult for 6 marks. I mean, let's try to draw it. So what we're going to have then, okay, hang on. Right, we're going to have a client. Yeah, we're then going to have a server. And basically, I mean, the server is then also going to have a digital certificate. So let's say, I don't know, digital certificate, right? Yeah, DC. Right, in this digital certificate, you're going to have a few things. One will be the public key. Right, yeah, key. And then another thing is going to be the digital signature. So if we think, well, the digital signature, this is used to verify the identity, right? So, well, we can say to authenticate, right? So it's going to use to be, well, it's used to authenticate the server. Because what you could have is, well, let's say you have someone else, right? They set up another server, and they try to impersonate this person. So yeah, this is like the sort of hacked, I know, yeah, the malicious server. Well, the problem is they're not going to be able to impersonate this server, right? Because their digital signature, is not going to sort of match, the real digital signature. Right. So well, then you have the public key, and I mean, well, let's just try and draw this. So basically, the client is going to send their initial request, just kind of asking, hey, like send over your digital certificate, basically. Right. So the server, I mean, let's kind of draw that. Right. The server is then just going to send its digital certificate. Right, so this is going to be the DC, and again, remember, this contains the public key, it contains the digital signature. Right, the client can then verify, so let's say verify the digital signature. Right, once it's verified the digital signature, and yeah, I guess you say, well, once it's happy that it thinks the server is, the real server, it's not some, malicious, malicious server impersonating. Well, then what it can do is it can then use this public key in order to encrypt some data. So yeah, let's say here, I mean, well, this will be encrypted. And again, right, because the server here has the corresponding private key, well, the server can then use this encrypted data, right, and then decrypt it, using its private key. So I think, I mean, this is what we have to explain. And like, so the thing with this, right, this is just one-way encryption. Now, if you wanted two-way encryption, well, then, I mean, right, then this one would also need some keys, right? And to be honest, I mean, the real way they would do this, well, there's a thing called like Diffie-Hellman. So yeah, I mean, you can search, Diffie-Hellman key exchange, but I mean, in a real system, again, you would probably want two-way communication, and yeah, that would be kind of the next stage of this. But I mean, I think, yeah, let's just try and write something simple. So let's say maybe the client will request the, let's say that, right? So the client will request, right, I'm just going to write this in kind of, short form bullet points. Right, the client will request, let's say, digital certificate from server. Right, well, let's say, right, server will send, right, let's say server sends, DC to client. Right, then we can probably say maybe client, right, so C, right, that's going to verify, let's say verify the digital signature in the digital certificate. Right, maybe, yeah, once, I don't know, yeah, once verified, I guess, or after verification. Right, then the client will use, right, let's say public key, right, from digital certificate, right, to encrypt and send, let's say to encrypt, I mean, yeah, so like here I guess we could say encrypt the message and send it as ciphertext. Yeah, I need to encrypt the plain text. I'm not sure if they would actually give us marks for saying plain text. Right, but encrypt the plain text, I don't know, maybe into ciphertext. Right, yeah, let's say and send to server. Right, I guess then you say the server uses, right, so it uses its private key, right, in order to decrypt. And then I guess we could mention, right, so, yeah, I know, like, if we want two-way or let's say two-way encryption, Right, two-way encryption. I mean, we can just say, well, then keys, I don't know, yeah, maybe then keys have to be exchanged. Or yeah, I think in particular, well, private keys have to be generated. Right, private keys will be generated. Yeah, I mean, so for, this Diffie-Hellman key exchange, right, is, I mean, it's more advanced, it's in A level. I mean, basically the way that works, I mean, the actual maths, I don't know. I mean, the formula, yeah, the exact formula, I'm not sure. Basically, it's using some sort of modulus. It's also using powers. So you do something like where you take one prime number and then, you raise it to another prime number, right, something like that. And then basically, using this, you can then generate a key securely. Because you have some value, you have something like big A, then you have, let's say, P. I guess, I don't know, maybe this one has, big B, maybe this has some other prime. Yeah, they then do this calculation, right? When they do this calculation, they can then, send over their result. This one sends over its result. And of course, yeah, based on this calculation, they can, they can both generate the same private key. And to be honest, you can do this in code. Like, it's literally like 5 or 6 lines of code, right? The calculation. So yeah, I mean, if you're curious about what this calculation is, again, just type in Diffie-Hellman like algorithm or Diffie-Hellman calculation, and then yeah, you can program this yourself. All right, but anyway, guys, I mean, I think that video's gone on super long, but well, as always, hopefully it was useful, and if it was, well, see you in the next video.